In this video, we will be solving some example problems on divide and conquer. We will specifically be solving the 4 problems from the third homework assignment, which are summarized over here. So let's start with the first problem here. This problem is asking us to modify the find element procedure that we talked about in the class. You would recall that this procedure was supposed to find an element of rank r, where r can be any number, in an unsorted array A in linear time. The way this algorithm, the standard way this works, is by finding first an approximate median of this array A, then partitioning the array around that approximate median, and then recursing in one of the halves, the lower half or the upper half. The way we discussed this in the class was to find the approximate median, where the algorithm divided this original array A into n by 5 groups, where each group was had at most 5 elements. The difference here is that this problem is asking us to modify that original algorithm by dividing the original array in groups of 11 instead of groups of 5. So that is the main difference. And here we will have to show that this algorithm still works in linear time even if we use groups of 11. So let's first remind ourselves the original algorithm, and here is the modified version. The only change in this algorithm here is that instead of using groups of size 5, we are using groups of size 11 each. So let's quickly go through this. The first thing this algorithm does is it finds an approximate median. To do that, it partitions the original array A into n by 11 groups, where each group has a size of 11. Having done that, it will then find the exact median of each of these n by 11 groups. Now notice that because each of these n by 11 groups have only 11 elements, finding the exact median of 11 elements would be O of 1 operation, constant time operation, because there are fixed number of elements. So that's the second step. We'll find the exact median of each of these n by 11 groups. Now because there are n by 11 groups, there will be n by 11 such medians. Now having found these n by 11 exact medians of all of these smaller groups, we will now find the exact median of this n by 11 elements. Okay, and this is done by recursively calling the same function find element r comma a. So this is the first step to find the approximate median. Now let's say the approximate median that is returned by this function is x. Okay, let's say this is our approximate median. So after this, what we will do is we will partition the original array A around this value x, such that, let's say this is your value x, this is the left half of the array, and this is, let's say, the right division or the right half. So this is AL, this is AR. Now this partitioning is such that all the values here in the left half would be less than x, and all the values on the right half, they are going to be greater than x. Okay, now depending on the rank of the element, this value of r, the rank of the element that we are looking for, will either have to recurse in the left half or in the right half. So there are 3 possibilities here, right? So let's say the size of this left half is such that it is exactly equal to r minus 1, right? Where r is basically the rank of element that we are searching. So if this is the case, it means the element that we are looking for is this x itself, because in this case x will have rank r, so we can simply return x and get done. So that's the first case here. The second possibility is that the size of this left half is such that it is greater than r minus 1. What that means is the value that we are looking for, it must be in the left half. Okay, so if that is the case, then we recurse in the left half, or this left division of the array. So in the left half, we'll be looking for this element of rank r. So we call the same function find element with this parameter r comma a on the left half. And so that's the second case. The third case here is that the size of this left half is such that it is less than r minus 1, right? What that means is the value we are looking for is in the right part of this division. So in that case, we'll again recursively call this find element function, but now with parameter r minus size of al minus 1 comma ar, right? So this is basically ar is the right division in which we need to recurse. And recall that because this element of rank r is now in the right half, the rank of that element in the right half would no longer be r, right? Because in this left half the values are starting from here, it is not starting all the way from 1. So therefore the rank of this element r that we are looking for would change to r minus size of this left half minus 1, because there are this size of al, so there are basically mod al plus 1 elements to the left of this value, this division. This is starting point of ar. Let's now think about the complexity of all of these operations. Okay, so let's start with this finding the approximate median. So partitioning the array into n by 11 groups, this is at max, so this is a constant time operation. At max this is linear time, it doesn't take more than that, right? So partitioning an array into fixed size groups is, this is a constant time or linear time operation. The second step, which is basically finding the median of each of these n by 11 groups, where each group has a fixed size of at most 11. So finding median of 11 elements is order 1 time operation, but because this has to be done for n by 11 groups, this will take order 1 into n by 11, which is basically O of n time total. Now the third step is find the exact median of array B by recursively calling this function. So notice that the size of input has the size of input here has gone down, right? So you see the size of this array B is n by 11. Okay, it's not n anymore, because we have partitioned this array. We are only considering the median of these smaller groups here in array B. So if the total time taken by the original input was tn, the time taken by this step would be t of n by 11. Now partitioning, we are using the partition function in quicksort, so that at most takes order n time, linear time, so partitioning would be order n. Now what about the last step, right? So if the element that we are looking for is x itself, then returning x here in this case is order 1, that doesn't take much time. Now the other two cases are slightly more involved. If you have to recurse in the left half or the right half, the complexity basically here, the overall complexity of step 5, it depends on which of these three cases, right? Which of these three cases would be most complicated or slowest. So let's think about what is the most lopsided partitioning that we can get around this value x over here. So let's arrange all the elements of the input in the grid format, where the elements are increasing top to down and then left to right. So let's say this is an element, this is let's just a second, right? So let's say this is our a of 1 comma 6, right? So this first column and sixth row. On top of this we have 1 2 3 4 5 elements, and then below also we have 1 2 3 4 5 elements. Now this is smaller than, let's say, a of 2 comma 6, so the elements are increasing, let's say, in the downward direction. So this will also have 5 elements on top, and then 5 elements here in the bottom. So continuing like this, this is, let's say, the median element. So the median element would be a of n by 22 comma 6, which will have 5 on top and 5 on bottom. And if we continue like this, the last column would be, this is the last column, which is a of n by 11 comma 6. Okay, so if we think about this, these values are decreasing to the left, and similarly here, let's say the values are increasing downwards, right? So this is greater, this is greater, greater. Let's assume that we have arranged the values like this in all these columns and rows. So if we look at this, if we focus on this median, the exact median of medians, this value over here, where would we find the smaller values, right? So all the values to the left here are smaller, and values to values above if you go up, right, so values above are smaller, right? So in this quadrant here you'll find the smaller values, right? So this is your smaller values. And if you're looking for larger values or greater values, then values to the right are greater and values below are greater, right? So basically in this quadrant here, these are all the values that are larger, right? So if you are doing an approximation, if you are looking for an approximate value, then approximately 1/4 n by 4 values, so approximately n by 4 values would be smaller, at least n by 4 values should be smaller than this, and approximately at least n by 4 values should be greater than the median element, right? So the most lopsided partitioning that you can get is n by 4 are smaller and 3n by 4 are greater, and this is an approximate computation. Obviously if we can be more precise about this. So this is going to be 1 2 3 4 5 6 elements, right? This is 6, and all the elements from here to here, this is n by 22, right? So the total number of elements here in this quadrant, if you want to be more precise, would be n by 22 multiplied by 6, which is basically n 3n by 11. Okay, so if you want to use this value, in that case the most lopsided partitioning that we can come up with would be 3n by 11 comma 8n by 11, right? So both of these are correct. We can use this approximation as well, and that's what I'm going to do here in this solution. But even if you have used this other partitioning, and you would still get full credit for this question. So let's go back here. So the recurrence relation should look something like this: T of n is equal to O of n plus T of n by 11 plus T of 3n by 4. Okay, which is basically the same as, so we can replace this O of n with C1n for some constant C1 plus T of n by 11 plus 3 T of 3n by 4. So we are assuming that there was the most lopsided partitioning in the worst case, and we had to recurse on the larger side. That's why we are assuming this, that's why we are using this 3n by 4, T of 3n by 4. All right, so now it is easy to show that this is actually linear. So one of the thing is, if you do n by 11 plus 3n by 4, this value comes to less than n, right? So which is basically a very strong sign that this recurrence should be linear. A very simple way of showing that this is linear is by using the substitution method. So we can assume that T of n is less than or equal to some constant c times n, okay, for some value of c. And now we'll try to find some inequality, some value of c for which this inequality is satisfied, and if that value of c is positive, then we would know that this assumption is correct. Okay, so let's assume that Tn is less than or equal to Cn, and now substitute this value Cn in this this recurrence over here, right? So we'll get C1 times n plus Cn divided by 11 plus 3 times Cn divided by 4 is less than or equal to Cn. Now we have to simplify this. So this basically implies that C1n plus so if we add this, we get 37 times Cn divided by 44 should be smaller than or equal to Cn, which is basically C1n should be less than or equal to Cn minus 37 times Cn by 44, which is basically 7 Cn by 44. Now we have basically C1n is less than or equal to 7 upon 44 Cn. So this n and this n cancels out, and this basically implies that C should be greater than or equal to 44 C1 divided by 7. So this for this range of constant C, the recurrence is going to be linear, right? So this basically shows that even if we partition the original array into n by 11 groups of 11 elements each, we still have the linear median finding algorithm. The second problem is a variation of the first problem. The only difference here is that instead of dividing the original array into groups of 11, we now want to divide it into groups of 3 for finding the approximate median. The question is basically to write the corresponding new recurrence relation and figure out whether the algorithm would still be linear or not. The modified algorithm is again presented here. It's exactly the same as described earlier. The only difference, like I said, is instead of partitioning the array A into groups of 11, we are now partitioning the original array A into n by 3 groups of size 3 each for finding the approximate median. That's median, right? That's the only difference here. So let's quickly dive into figuring out the complexity of doing each of these operations, right? So once again, partitioning the original array into n by 3 groups would be constant or at most order n, which is linear. For finding the median of each group of size 3, because each group is of size 3, finding the median of individual group is order 1. It's a constant time operation. And now because there are n by 3 groups, so you'll have to do this n by 3, which is basically order n total. Now recursively finding the median of array B, whose size is n by 3, if the original problem required t of n time, this problem would require t of n by 3 time. Okay. Now let's say x is our approximate median. So once again partitioning the original array A around x would be order n, linear operation, because we are using the quicksort partitioning. Now after this, the last step is again recursing, recursing either on the left half or the right half of the division. So recall that we have divided the original input around the partition, the pivot x, where this is the left half and this is the right half, and all the values in the left half are less than x, and all the values in the right half are greater than x. Once again, the complexity of this step 5 would be dependent on the slowest of all of these three operations. So based on what is the most lopsided division or partition of this original array that we can come up with, that would determine the complexity of this step 5. So let's figure out what is the most lopsided partition that is possible here. So let's again arrange the original elements in the format of grid. So right now in each array we'll just have three elements. So let's say this is the median of this array. So there would be two more items, and let's say this is a2 comma 2, which is the median of this second subarray, and then there are two other elements here. If we go on like this, here is, let's say, the exact median of all these medians, which would be basically n by 6th column, second element there, and then there will be one element above and one element below. And if we keep going, this is the last element here, which is the n by 3th column and the second row. Okay, so once again, let's partition this entire grid across this exact median of medians. Now notice that if we go down, the elements are small, and if we go to the left, the elements are smaller than this median element. So we find the smaller elements here in this quadrant. So this is smaller, all the elements that are definitely smaller than the median of exact medians, and all the elements that are greater would be above and to the right. So this quadrant here, this is certainly the larger elements, right? So now here there is one important thing that you should notice, right? So I know that some of you might have used the approximate division, that in this quadrant there will be approximately 1 by 4th, right, n by 4 elements, and in this quadrant there will be approximately n by 4 elements, right? So the most lopsided partitioning would be n by 4 comma 3 n by 4. You will get full credit even if you have used this partitioning. However, if you notice, this is not actually a very good approximation for this particular scenario, and that is because so that is because when we find the exact division, the exact number of elements in this that can be smaller or larger, you'll see that we'll come up with a value that is smaller than 3n by 4. So 3n by 4 is not a good approximation here, especially because we will ultimately see that the complexity of this new algorithm after partitioning into subarrays of size 3 is going to be greater than linear time. But anyways, for this homework assignment, you will get full credit even if you have used this. All right, so the exact number of elements that are smaller is, if you think about this, there is 2 elements here, and in this row from here to here there are n by 6 elements, right? So the total number of elements that should be smaller is n by 6 multiplied by 2, which is basically n by 3, right? So which implies that the most lopsided partitioning that you can have is n by 3 comma 2n by 3. Notice that 2n by 3 is smaller than 3n by 4. Okay, so for this solution over here, I'm going to use this more accurate version of partitioning. So let's come up with the recurrence and solve this. Would be something like this. We have t of n equal to O of n plus t of n by 3 plus t of 2n by 3. This, so we are assuming once again the most lopsided partitioning of array around x. Now notice that n by 3 plus 2n by 3 is exactly equal to n, right? So this is actually an indication that this recurrence is very likely not going to be linear. But in any case, let's assume that this is linear, right? So let's say this is same as c1n plus t of n by 3 plus t of 2n by 3, right? So let's assume this is linear, and therefore let's say there is some constant c for which c times n is always greater than or equal to the recurrence. Okay, let's now use the usual substitution method to figure out whether any such positive constant c exists. So we have t of n smaller than or equal to c of n, which implies substituting this value here in the recurrence, we get c1n plus cn by 3 plus 2 times cn by 3 should be less than or equal to cn. Right, now let's see whether we can find such a positive constant c for which this inequality holds. If we simplify this, we'll get c1n plus cn is less than or equal to cn, which basically, so basically this cn and cn cancels out, so this basically implies that c1n should be less than or equal to 0. So essentially this is possible only if c1n is negative or 0, right? Now, which is obviously a contradiction, because this c1n represents the linear time work that our algorithm is doing for, let's say, partitioning. Obviously the work that we are doing, it cannot happen in negative time. So so there is no such positive value of c for which this inequality holds, right? So this is not linear based on our substitution method. Let's also see what happens if you use the other approximation, right? So let's say you assume the lopsided partitioning of n by 4 and 3n by 4. In that case, your recurrence would look like this. You have O of n plus t of n by 3 plus t of 3n by 4 equal to is less than or equal to some cn. Okay, so this basically implies that c1n plus substituting the cn here in the recurrence, we get cn by 3 plus 3cn by 4 should be less than or equal to cn. Notice that this c1n is basically representing O of n, some linear time work. So let's simplify this. So this is equal to c1n plus if we add this, we get 13 times cn divided by 12 should be less than or equal to cn. If you basically take this to the other side, you'll find that this means c1n should be less than or equal to minus cn by 12. So this n and this n cancels out, so this basically implies that c should be less than or equal to minus 12 times c1. Now notice that this is a negative value, so there is no such positive value of c for which this inequality holds, and hence this recurrence is not linear. In fact, it is possible to show that the original recurrence that we came up with, Tn is equal to C1n plus T of n by 3 plus T of 2n by 3, this recurrence is actually O of n log n. This belongs to the O of n log n. We can actually prove this using the substitution method, right? So let's try to do that here quickly. So let's assume that this recurrence C1n plus T of n by 3 plus T of 2n by 3, this is less than equal to C times n log n for some value of n and some positive constant C. Let's now substitute this result Cn log n into these recurrences over here and then solve for some constant C. So we'll get C1n plus Cn by 3 log of n by 3 plus uh, 2 2c by 3 n log of 2n by 3. This should be less than equal to C times n log n. So this basically implies that C1n plus, if let's take this Cn by 3 common from here, so we get Cn by 3 times log of n by 3 plus 2 times log of 2n by 3, right? This should be less than equal to Cn log n. Okay, so this once again, let's rearrange the terms inside the bracket. So we'll see C1n plus Cn by 3, and this can be written as log of n by 3 plus this would become 2 times log of 2 plus 2 times log of n by 3. This should be less than equal to C times n log n. Okay, and now basically from here onwards it should be fairly straightforward to simplify this. So this basically becomes C1n plus Cn by 3, and these terms inside, they become 3 times log of n by 3 plus 2. So log 2 is simply 1, so this will simply become 2. This should be less than equal to C times n log n. Okay, this n basically is common in the left and the right side, so this cancels out. So this becomes C1 plus so let's open this bracket. So this will become C times log n by 3 plus 2c by 3. This should be less than equal to C times log n. So this is basically C1 plus 2c by 3 should be less than equal to C times log n minus C times log of n by 3, which is basically simply C times log 3, right? Because this basically log a minus log b basically means log of a divided by b, right? So this is how it reduces. Now if you rearrange these terms further, you'll find that the final result, this inequality would result in C should be greater than equal to C1 divided by log 3 minus 2 by 3. So this is your answer. Now this is going to be positive because if you're considering log 2 base 2 of 3, this is going to be greater than 1. This term is going to be greater than 1, and 2 by 3 is smaller than 1, right? So this quantity on the right hand side, this is going to be a positive quantity, which basically shows that the recurrence that we come up with was O of n log n. So the third question here is asking us, what is the naive complexity of computing 2 to the power n for any value of n, and then how can we reduce this complexity, this naive complexity, to order of log n, right? So first of all, the naive complexity of computing 2 to the power n is actually O of n, right? So it's very simple to see this, right? So let's say you want to compute 2 to the power 8. So the naive way of doing this is 2 multiplied by 2 multiplied by 2, right? And so on. Do this uh, 7 times. So this is basically So this is 2 to the power 8, right? So you are doing 1 2 3 4 5 6 7 multiplications, right? So which is basically order of n for doing 2 to the power 8. Now the question is, how can we reduce to order of log n? Now actually there are multiple ways of doing this. One simple way of doing this is notice that whether we actually need to do all of these multiplications, right? So for instance, let's say we use divide and conquer in some way to do this 2 to the power 8, right? So basically, let's say at the bottom here we are doing so let's say at the bottom of the recursion tree we are doing, so we pair these up, right? So this two, this two, these two multiplications, these two multiplications, right? So at the bottom of a recursion tree we have these four products, right? So we multiply this here, and whatever result we get, we'll get 4 here and 4 here, right? And here we'll do 4 into 4, and then again here for these two pairs we'll do 4 into 4, and finally on top here we'll do so we'll get 16 from here, right? And 16 from here, and then here we'll do 16 into 16 to get the final answer 256, right? So once again, if you are doing this division into this recursive division naively, you again end up doing 7 multiplications, right? So this is 1, this is 2, 3, 4, 5, 6, and 7 multiplications. But if you are smart about this, notice that there are a lot of repeated operations, right? So for example, here you are doing the same computations 2 multiplied by 2 4 times, 1 2 3 4 times here, right? So what if you do the computation actually only once? So you do this 2 into 2 4 only once, and then because you all these other computations are exactly the same, instead of doing this computation again, you simply use the value, this computed value here in these other three cases. So for this bottom level of this recursion tree, you ended up doing just one multiplication. Similarly here, because you are doing the same, exactly the same operation 4 into 4 twice, instead of doing that twice, you do it once, you compute this value 16 once, and then for the second time, instead of actually computing 4 into 4, you just use this computed value of 16 here. So again, at this second level of recursion, again you end up doing just one product, and on top again, now there is only one product, so you will have to do this, there is no repetition, so you do this one more multiplication here. So notice that if you do this, if you were remembering the results of your multiplication, then you end up doing simply 1 plus 1 plus 1, which is 3 products instead of doing 7. Okay, so log2 base 2 of 8 is actually 3, so this is log n number of products. So one possible trick here is, instead of doing the same operations repeatedly, do a repeated operation once and then remember the result, and for other instances of the same problem or same sub problem, just use this remembered value. That can help you do this computation in log n time. Okay, so if you were doing this, let's quickly write the recurrence relation for this. Let's say the original problem requires t of n times, right? Now you divide this problem into two halves, t of n by 2 and t of n by 2. Okay, and you solve these two halves and then combine the result. Okay, now what we are doing by remembering the answers for identical parts, essentially here, instead of solving both the parts, we will end up solving just one of the halves, let's say this one, and for the other one we'll just remember the result and use it as it is. Okay, so the complexity of doing this is tn is equal to t of n by 2. Notice that it is not 2 times t of n by 2, because you are only solving one half, and then you in constant time you are applying that result to the other identical half. So this is actually your recurrence, and from Master's theorem you will see that this is theta of log n. Okay, now just to be clear, you can compute 2 to the power n like this. If your n is even, then you can simply say 2 to the power 2 to the power n by 2 multiplied by 2 to the power n by 2 for even n, right? Otherwise you could say 2 to the power n minus 1 divided by 2 multiplied by 2 to the power n minus 1 divided by 2 multiplied by 2. Okay, if your n is odd. So this is how you can do this computation. There are other ways of doing this, but this is one of the simple ways. So this problem over here, the fourth problem, is actually a variation of the maximum subarray problem that we talked about in the class. So here once again we are given a list of n prices for a given stock, and each price basically represents the closing price of the stock for a given day. So for example, maybe on day one it closed at price $10, right? On the second day maybe it closed at $9, then maybe on the third day it closed at $14, then maybe it closed at $17, and then maybe on the next day it closed at again at $11 and so forth, right? So we are given these closing prices for a given stock for a period of n days, and what we can do is we can buy this stock only once and sell it once over this n day period, and we have to determine when should we buy the stock out of these n days and when should we sell it so as to maximize our profit. Notice that when we solved this problem in the class, we modified this data so that we came up with a new array which represents, instead of representing the closing prices, it represented the difference between the price, the closing price on the ith day and I minus 1th day, right? So that this problem can be transformed into the maximum subarray sum problem. However, here in this problem, the problem specifically says that you cannot transform this data in any way, so you have to use the prices as they are given, and now you have to come up with a divide and conquer algorithm for solving this problem. Now once again, the problem is the solution is very similar to what we came up with. So for instance, this is your array. Let's say this is your low index, this is your high index. So the solution methodology remains the same. We divide this array into two parts of n by 2 size, and then we recurse on the left half. So we solve this problem here and we recurse on the right half, and then we finally combine these two costs. So there are actually three possibilities. So the first possibility is that the days in which we should buy and sell, they are completely contained in the left half. The second possibility is that the days that we should buy and sell, they are completely contained in the right half, the right subarray. And the third possibility, so this is the first possibility, the second possibility, and the third possibility is that maybe the day when we should buy is in the left half, and the day when we should sell for maximum profit is in the right half of this division, right? So this is the third case. So the first two cases can be captured by divide and conquer, but this third case where the buy and sell days they cross the boundaries of the division, this must be captured as merge cost, the merging cost of the solutions. So here is the algorithm. It is a very simple modification of the algorithm that we had seen in the class. So essentially this is the function find max buy sell days. It takes three parameters, the array A and the low index and the high index of the array, as we have seen. So this is our array. This is the, let's say, the low index, this is the high index, and this is our array A. Now the base case here is that there is only one element, right? So if high is equal to low, it means there is only one element, there is only one day, and basically if there is one day, you cannot make any profit by buying and selling, so you simply return the low, the high, and the profit will be zero for buying and selling on the same day. This the second case here is, this is the recursion. So if there are more than one elements, then we basically divide, we find the middle point. So let's say this is our midpoint here. So we find the midpoint by basically taking an average of the low and the high, and then we recurse on the left half. So the left half, the right half. So this is the first case where we are recursing on the left half, which is, so this is the first case. So we have passed the left subarray, so we passed the original low as the low, but we have passed the mid as the high, right? So we are recursing on the left half here. The second case here is recursing on the right half, so we have passed the original array, but mid plus 1, which is basically this location here, this is the low for the right half of the array, and high remains the original high, right? So this is basically the right half. So these are the first two cases, the recursion cases, And the third case is what if the buy and sell they occur in the different halves. So in that case we have this third function call, which is find max buy sell crossing days, right? So this is not a recursive call, this is a separate call which takes 4 parameters, right? So it takes the array A, the original array, as a parameter, then the low index, the mid index, which is basically this one, and the high index of this original array to figure out what are the best days to buy and sell in the left and the right half of the solution. And finally, once we have so basically each of these three function calls returns three things, right? So let's focus on this the left half here, right? So basically it will tell this function will return what is the index of the best day when we should buy in the left half, what is the index of the best day in the left half when we should sell, and then by doing this buying and selling in the indicated days here, what would be the profit, the maximum profit that we can get in the left half of the array. Similarly, we have the index for buying in the right half, selling in the right half, and then what is the maximum profit we can make from this purchase and sell in the right half of the array. So these are the three things that these two recursive calls return. The third call here, this also returns the same three things. So what is the index of the day in which we should buy if the buy and sell are happening in different halves? What is the index of the day when we should be selling? So notice that this buy that is written by find max buy sell crossing days, this would be in the left half, this would be in the left half, the sell day should be in the right half, because these days are supposed to cross this mid boundary. And then what is the total profit that you can make by doing this purchase and selling? So these are the three data points that are written by these function calls. Now after this, once you have these three pieces of information, the final answer is pretty straightforward, right? So we simply check if the left profit is greater than equal to right profit, and it is also greater than equal to the crossing profit, then we simply return the answer written by the left half. Otherwise, if the right profit is greater than both the left and the crossing profits, then we simply return the answer from the right half of the array of the recursion. Otherwise, if the first two cases are not true, then we simply, it means that the buy and sell should happen in the different halves, so we just return the answer returned by find max buy sell crossing days. So this recursive solution is pretty straightforward and simple. Now one more thing that you need to understand here is how exactly do we solve the third case where the buy and sell should happen in the different halves, right? So the first two cases, these are pretty straightforward, these are recursive calls. But how do we solve this third case? How do we figure out when should we buy and when should we sell to maximize our profit if this buy and sell is happening in different halves of the array? Now this is actually, if you think about this is pretty straightforward. If I tell you that you must buy in the left half and you must sell in the right half, then what would you do? An obvious strategy to maximize your profit would be to find the day with minimum price in the left half and to find the day with the maximum price in the right half. That's it. Once you do that, that is going to be your answer. And this is exactly what this function find max buy sell crossing days does. This function is given over here. As you can see, the function is simply in the left half of the array, it is simply going from the midpoint all the way to low, from mid to low. So basically, if this is your array, this is your mid, this is your low, this is your high, right? So from mid to low, it is simply finding the minimum value. It is the pointer is going from mid to low and looking for the minimum value in this array, and it is keeping track of the minimum value that is found and what is the index of that minimum value. Similarly, on the right half, it is going from mid all the way to high, and it is keeping track of the maximum value, and it keeps track of the maximum value as well as the index of the maximum value. And in the end, it simply returns the index of the minimum value in the left half, the index of the maximum value in the right half, and then the profit, the right max minus left min. That's it. It's a very straightforward algorithm. Alright, so this brings us to an end of this discussion. I hope these video solutions were useful. If you have any further questions, please feel free to email me or stop by my office hours. Thank you.